Okay, now over to matrix arithmetic. I've imported Numpy as NP and I have two variables here, x and y, and I have created matrix using np.matrix. And now this might seem different from what we had been doing in the previous lectures, and indeed this is different. Instead of creating an ND array, I have created a matrix, a matrix class, and if you see in the next line, it is a numpy.matrixlib defmatrix.matrix, and this is not an ND array. And while many of these matrix computations can be carried out on ND arrays, it is advisable to create matrices which are strictly two-dimensional as compared to the n-dimensional ND arrays, because the former, that is the Numpy matrices, provide a convenient notation for matrix multiplication, and they also allow us to carry out some matrix arithmetic specific tasks. So let us look at addition. Now addition is carried out on an element by element basis. So as you can see in the second row, I have two matrices, A1, B1, C1, D1, the second matrix with A2, B2, C2, D2, and the addition and even subtraction, they are carried out element by element. So the element present in the first row and the first column of matrix 1 is added to the element present in the first row and first column of matrix 2, and so on. And this is essentially what Numpy has done for us. One plus 5, 6, 2 plus 3, 5, 3 plus 8, 4 plus 7, 11, 11. In scalar addition, the scalar or the constant is added to all the elements of the matrix. So it's the same as it happens in the vector, but obviously in vector it's a one-dimensional entity, whereas in matrix we end up adding our constant or scalar to all the elements present in the matrix the way you see. So x plus 3, 1 plus 3, 2 plus 3, and so on. And the same happens in the case of scalar multiplication. 3 was multiplied by all the elements of this particular matrix, 1 into 3, 2 into 3, 3 into 3, and so on. The subtraction is also done in an element-wise manner, and you can see x minus y. 1 minus 5 is minus 4, and so on. Now multiplication can be a slightly complex affair, and I've created a very simple matrix A, 1, 2, 3, 4, and this is a 2 cross 2 matrix, which means it has 2 rows and 2 columns. And now I'm going to carry out head marked multiplication A star A. And this is the output we get. You can compute this by hand, but in order to get this 7, the first row was multiplied by the first column and added 1 into 1 plus 2 into 3. Then for this, the first row was multiplied by the second column, and that is how we get the 10, and so on. And for this one, for this particular element, we are going to multiply the second row by the first column, and so on. The way we did element-wise subtraction and addition, we can even do element-wise multiplication. So it is going to be np.multiply, and as you can see, it is going to be 1 into 1, then 2 into 2, 3 into 3, and so on. And we don't have to multiply the matrices with each other. We can have, say, variable b with a different matrix, and even that multiplication would work. Then here are some very specific matrix arithmetic specific computations, inverse and transpose. For transpose, let's just look at transpose first. We flip the rows with columns, and for that I specify the variable storing my matrix, which is a dot t, and this dot capital T will flip the rows with columns, because this is how you take the transpose. In order to take the inverse, from Numpy ling lang we import inverse inv, and then we actually take the inverse by specifying inv inv a, and we get the inverse of our matrix. And these are some of the very basic computations that can be performed very easily using Numpy. And this is not a course for matrix arithmetic, but should you need to explore matrix arithmetic in more detail, then Numpy is the tool for executing these computations.